All right, I have a feeling you already know what a mesh is. A mesh is a loop with no other loops inside of it. And a mesh current is the current that exists in the mesh. So a mesh current has a reference direction associated with it. However, its value is unknown, and its value is typically what you solve for when you solve a circuit. Now here's something you need to know about mesh currents. Mesh currents are totally fictitious quantities, but they are very useful. You define these fictitious mesh currents, and then you solve for those mesh currents. Let me kind of explain what that means. In a typical KVL, KCL type of circuit, let's say we've got a circuit that looks like this, a pretty simple one. So here's our circuit, and now let's define 3 currents that would be part of a KVL, KCL type problem. All right, so we've got these 3 currents, and if we were doing a typical KVL, KCL problem, we would have to have 3 equations to solve for the 3 unknowns here. And we would write a KCL for this node right here that would look like this. I1 is equal to I2 plus I3. All right, but you could do something like this. You could take I3 and write it in terms of I1 and I2. In other words, I3 is I1 minus I2. That's I3. That's nothing but solving this equation here for the variable I3. And then anytime that you have to write I3, anytime that you would like write a loop equation and you would normally write I3, if instead of writing I3 you wrote I1 minus I2, well, that would remove one of the variables from the equations, and it would simplify matters. That is essentially what the mesh current method does. It defines currents, and then you use those currents to solve. So for a problem like this, we could redraw it this way. Instead of defining the 3 currents I1, I2, and I3, let's just define 2 currents down here, the mesh currents. And we'll say, well, that's a current that goes around this mesh, and we'll call that I sub A. And here's a current that goes around this mesh, we'll call that I sub B. Now, if you're comparing these two right here, I sub A is the current that's in this outside portion here, and that's essentially I1. Over here on the right-hand side, I2 is the current that goes through this outside branch here, and this is I sub B. So I sub B is essentially I2. But what about through the center here? Well, if we're talking about a current going down, then this current through the center would be I sub A minus I sub B. If we were talking about a current going up, though, it would be I sub B minus I sub A. So you see, in this area where the 2 currents overlap, instead of calling it I sub A, I sub B, or I1, 2, 3, whatever you want to call it, instead call it I sub A minus I sub B if it's going down, or I sub B minus I sub A if it's going up. That, believe it or not, simplifies matters a lot and allows you to solve a problem with a significantly fewer number of equations. And I'll show you how to do that right now. Let's do an example. All right, so here we've got this circuit, and what we want to do is we want to solve for the voltage across the 8 ohm here. Let's call that V naught. Okay, find V naught. And we could also calculate the powers for the 2 sources. For example, power for the 40 volt is what? Power for the 20 volt is what? And then V naught, what is that? Let's use the mesh current method to solve for this. So the first thing is to define our mesh currents. We have 3 meshes here, so we need 3 mesh currents. And we can easily do that. We can go any direction we want, but let's just go around this way and say that that is I sub A. This current throughout this mesh is I sub B, and this current throughout this mesh is I sub C. All right, now that we've done that, we can write KVL equations for each of the 3 meshes using I sub A, I sub B, and I sub C. So let's do for this leftmost mesh. we are going to start in the upper left-hand corner and go clockwise here. Now, here's an important thing you're going to notice. If you always go in the direction of your current, then everything is going to be a drop through the resistors. And we've drawn all of the currents going clockwise here. If I go clockwise, then everything's going to be a drop. So you might want to call a drop positive in this case so you don't accidentally drop a sign, but you can also call it negative. It'll work either way. Let's stick to our convention and call drops negative. So as I go through the 2 ohm, minus 2 I sub A. Now through the 8 ohm, minus 8. And here the current is I sub A minus I sub B. And then we go up here and we're going to have a rise when we go through the 40 volt. So that's plus 40 equals 0. So there's the left loop equation. Let's do one for the center loop now. Starting in the upper left hand corner, going clockwise, minus 6I sub B, minus 6 I sub B minus I sub C, and then minus 8 I sub B minus I sub A, and that's equal to 0. So those are the 1, 2, 3 elements. This is the voltage across the top 6 ohm. This is the voltage across the side 6 ohm, and this is the voltage across the 8 ohm here. Okay, so that's the center loop. Now let's do the right loop equation. Start in the upper left hand corner and go clockwise, minus 4 I sub C. Now we're going to have a drop across the 20 volts, so that's minus 20, and then a continue on, a drop across the 6 ohm, and in this case it's I sub C minus I sub B, and that's equal to 0. Now notice this term here is the voltage across this 6 ohm. This term here is also the voltage across the 6 ohm. And you might say, well, if we were doing KVL, KCL, then one of these would be a drop and the other one would be a rise when we pass through it. But notice the sign has been switched because we've taken this I sub B and I sub C and reversed them. All right, now we can rearrange terms, multiply through, rearrange terms, and collect similar values. So let's do that. We have I sub A. Looks like we're going to have negative 10 I sub A and 8 I sub B, and then no I sub C's. Let's leave a blank there for I sub C's though, and we'll put the 40 on the other side. Then it becomes negative 40. Now for this one, looks like we're going to have 8 I sub A's. We're going to have, let's see, negative 6 and negative 6 and negative 8. So that's 12 plus a 20. So that's negative 20 I sub B. And then I sub C looks like we're going to have plus 6 I sub B. And that's equal to, there are no constant terms over here, so it's equal to 0. All right, let's go now to the third one. No I sub A's, so let's put a 0 there. I sub B's, looks like we've got a positive 6 I sub B. And then we've got a negative 6 here and a negative 4 there, so that's going to be negative 10 I sub C. I think I just made a mistake. That should be I sub C there. I caught that. And then we've got this negative 20 over here. When we put it on the other side, it becomes positive 20. All right, there we have our 3 equations with our 3 unknowns, I sub A, I sub B, and I sub C. You need to solve those. And whenever you solve those, here's the answer that you get. Those are your I sub A, I sub B, and I sub C values. Now that we've got those, we're still not finished. We need to figure out what the power for the 40 volt, the 20 volt, and V naught is. Let's start with the power for the 40 volt. By looking at the circuit here, I see the current is going into the negative terminal. So rather than writing P equals IV for the 40 volt source, I need to write P equals minus IV. Now the V is going to be 40 volts, and the I is going to be I sub A. So this is going to be minus I sub A times V of 40 volts. Do that multiplication and you end up with negative 224 watts. So there is the power of the 40 volts, and it's negative. That means that the 40 volt source is delivering energy. All right, let's do the same thing for the 20 volt. Ask yourself, do I need to write P equal IV or P equal minus IV? Since the current is going into the positive terminal, it's just going to be P equals IV. So I times V. What is the I? Well, the I is I sub C. So it's this right here. So it's minus 0.80 amps times V of 20 volts. And that turns out to be negative 16 watts. So negative 16 watts, the negative sign indicates that it is delivering energy. So both of the sources are delivering power. Okay, we're still left with V naught. Let's see if we can figure that out. V naught is either going to be I times R or minus I times R. Look here. If we talk about the current entering the top terminal, that's I sub A, then we would write V naught equals I times R. But if we talk about the current I sub B, which is entering the negative terminal, then we would write V equals minus IR. All right, so which one do we use? Well, let's consider the current to be going into the top, into the positive. That way we write V naught is equal to I times R. But what is the I? Well, since we're talking about what's going into the top, that's going to be I sub A minus I sub B. So that's the current. And the R is 8 ohms. So we'll plug in for I sub A and I sub B. 5.6 amps minus 2.0 amps multiplied by 8 ohms, and that turns out to be 28.8 volts. So that's V naught right there. We've now found what we've set out to find, so this problem is finished. All right, then let's do another one. All right, this is the problem. What we're after is the power of the 80 volt source. It'll be delivering power. It's the only active element here. And then what is the power that's dissipated by the 8 ohm resistor as well? So in order to figure out this power, we're going to need the current going through it. So we'll define one of our mesh currents to be that. That'll be pretty straightforward. And then we can do the same sort of thing with this if we know that current that's going through the 8 ohm. All right, next step is let's define our mesh currents here. So we'll call this one I sub A. The current around the top here, let's call that I2. I want to change this to I1. So that's I1, this is I2. That way I'm consistent with my notes that I'm looking at here and I don't screw up. And this is I3. All right, so those are our mesh currents then. We're ready to write our loop equations then. So for the one loop, that's this one with I1 in it, let's start here in the upper left-hand corner and go clockwise. Minus 5 times the current through that. Well, we're going in this direction, so it's going to be I1 minus I2. And then when we go this way, it's going to be minus 26 times I1 minus I3. And now we go through this 80 volt source, and that's a rise, so plus 80 equals 0. There, I think we've just done that one. Let's do the same thing for loop 2 at the top. So that's going to be minus 30 I2, then through the 90, minus 90 I2 minus I3, and then through the 5, minus 5 I2 minus I1, and that's equal to 0. And then for loop 3, starting in the upper left-hand corner, going clockwise, minus 90, I3 minus I2, and then minus 8, I3, and then minus 26, I3 minus I1. And that's equal to 0. All right, I believe that we've got all of these. All right, so it looks like we've got all of those. Now let's multiply through and gather our like terms here. Starting with loop 1, looks like I've got negative 5 I1s and negative 26 I1s, so that's going to be 31 I1, and it's going to be negative. And then I2s, I've got positive 5. And then for I3s, I've got positive 26. And then this 80 on the other side of the equal sign becomes negative 80. Okay, and then for loop 2, let's see, I'm going to have positive 5 I1s. And then I2s, I've got 30, 90, that's 120, 125 I2s, and those are going to be negative. And then I3s, looks like I've got positive 90 I3s. There are no constants here, so that's equal to 0. All right, we're ready for loop 3 then. Let's see, for I1s, I'm going to have a positive 26. For I2, there's positive 90. That's it. So, and then for I3s, 98 and 26. That's going to be negative 124 I3s. And that's equal to 0. Okay, at this stage you've got 3 equations, 3 unknowns. You should be able to use the techniques that you know in order to solve for the 3 unknowns. When you do that, you get I1 equals 5 amps. I2 is equal to 2 amps, and I3 is equal to 2.5 amps. Okay, now that we've done that, we're ready to go back up here and figure out what our power for the 80 volt source is and power for the 8 ohm resistor is. I'm going to move down to another sheet of paper. The power for the 80 volt source, I need to either write P equals IV or P equals minus IV. I look at the current, it's going in through the negative side. So that's going to be P equals negative IV. So P equals minus IV is going to be the form of the equation. Now for the I is I1, so that's 5 amps. And the V is 80 volts. So that's going to be 400 minus 400 watts. There's the power for the 80 volt source then. And you notice it's negative, which means it's delivering energy. Now let's do the power for the 8 ohm. Look at that. Do I write P equals IV or P equals minus IV? Doesn't really matter because it's an 8 ohm resistor. It's always going to be dissipating energy. So it's always going to be absorbing and never supplying energy. So the way to approach this is use I squared R. So I going into it is I3, square it, and then times R of 8 ohms. So I3 was 2.5 amps, so 2.5 amps. Doesn't matter if it's positive or negative because you're going to square it. Multiplied by 8 ohms, and that turns out to be 50 watts. And you'll see it's positive, but it would be positive even if we would have gone through the trouble of figuring out what the voltage polarity was over this first. You cannot decide just looking at this whether or not you need to write P equals IV or P equals minus IV. You need to determine what the polarity of the voltage is across this. And there's some work involved in doing that. But if you use I squared R, You don't have to worry about it. You're going to end up with a positive answer no matter what I is. All right, so there you have it. We have figured out what the power was for the 80 volt source and the power for the 8 ohm resistor. And that's what we were asked to solve for, so we're done with this problem. And I think that pretty much covers everything you need to know about the mesh current method. It's pretty straightforward, pretty easy. If there happened to be a dependent source in here, all the dependent source does is it adds one more constraint equation. So you would just have to come up with one other equation, and oftentimes it's kind of obvious what that equation should be because you're almost given it as part of the problem. Nevertheless, it's pretty straightforward. I'm going to leave it at that. Now we are finished with the mesh current method.